Hello, and welcome to the virtual Partition and Distribution Coefficient Lab. You will have already had a lecture from me about partition and distribution coefficients, but simply put, the distribution coefficient of a molecule is how much it will distribute itself between two solvents. Typically, this will be looking at something like octanol and water or dichloromethane, as we'll be using in this lab, and water. We might do that for a range of reasons, but typically, and in my experience, these distribution coefficients are mainly used to predict where a drug is going to partition in the body after it's been absorbed, or indeed if it will be absorbed, particularly after oral administration. Log P can be thought of as a special case of log D. So log P is the log value of the ratio between the amount of drug that can be found in the organic solvent, so DCM or octanol, over the amount of drug that can be found in the aqueous solvent, which will be water typically. And this has to be in the unionized form. So the log P must be taken at a pH where the molecule you have is in its unionized form. Now that may not always be possible, in fact, but that's the idea of log P. So you get the concentration of drug in water, the concentration of drug in an organic solvent, such as octanol, if you want to look at the body, or DCM. The ratio between two of them is then you take a log of it, and that gives you your log P value. Now these are useful as a direct comparison between molecules, so you can see which one maybe is more lipophilic than another. But as I said, that's a special case of log D. Now log D doesn't have to be an unionized form of a drug. So that literally is just the distribution coefficient. So you have the amount of drug that's in the organic phase at the top, so octanol or DCM as I've been using, and then underneath that you divide that by the concentration or the amount of drug in any form in the aqueous phase. So ionized and unionized in any form. And that can tell you, if you do it at different pHs, where a drug will partition itself in lots of different environments. And whilst it's a lot more information to gather, it's actually really useful. It's particularly useful when you consider, after you swallow a drug orally, that it goes through quite a different range of pHs through your gastrointestinal tract. So it will go into your stomach, where you'll have a very acidic pH, 1 to 2, through to your intestines, where it will get neutralized by sequestrants and bile and things like that, all the way through to a more alkaline pH and a neutral pH as well. So we've got a whole range of different pHs at which drugs will be ionized differently, which, as you know, will affect whether it will be absorbed through your gastrointestinal tract or not. So in the lab, I'm just going to go through taking a partition coefficient, a log P of trimethoprim, using DCM and water, acidic water in this case, slightly acidic to make sure it's unionized. But then we'll be looking at some more example data to see how it's useful to be able to look at log D and information that tells us and how it's applicable in the real world as well. We're ready to get going with the practical part of this lab, and you can see that I'm in the fume hood, and that's because we're working with dichloromethane. So predominantly we will be working with the DCM inside the fume hood as much as possible, although I will need to use the sonicator bath in just a moment, so I will have to come back out of here and just show you that. So first of all, we've been asked to weigh out 0.5 grams of trimethoprim. I don't think I need to show you that, so I've already done that, half a gram of trimethoprim there, 500 milligrams. And that needs to be dissolved in 100 millilitres of dichloromethane. So, take my measuring cylinder, and I'll take my dichloromethane. So 100 millilitres is exactly what I've got here. I'm going to work within the hood to do this, and get it up nearly up to the 100 millilitre mark, and then I'll be able to move in and get that up to eye level for me. to accurately measure 100 millilitres. Okay. Now I need this in a vessel that I can seal and that I can securely put into the sonicator. I'd rather not sonicate DCM without any lid on when I go and put it in there. So I'm actually going to do that in one of the volumetric flasks. Ideally, you might want to do this in a round bottom flask. I just happen to have the volumetric flask to hand here. And then I will move over to the sonicator and talk briefly about how to safely use that. Now we need to use the sonicator because trimethoprim, whilst it is soluble in dichloromethane, it's not a fast process. And so we're going to do that to speed the process up. And once this is all in, because I'm in a volumetric, may as well do it really accurately. And we can see that we've actually got to 100 millilitres. So we're going to move over to the sonicator bath and then just have a quick talk about the sonication. So we're going to give this a little bit of gentle sonication. So yeah, it's dichloromethane with 0.5 gram of trimethoprim in there. I don't know if you can see this on camera, but we've got essentially a snow globe there at the moment with the solid drug not fully dissolved. Now, using a sonicator bath is obviously straightforward and quite simple, but just a couple of things to point out. You'll see that I've got a retort stand, a bottom clamp set up here, so I don't have to hold this flask in the sonicator bath. Now, whilst that is very useful, so I don't have to stand here, that's great. It's also because it's dangerous to put your hands into a sonicator bath. So the ultrasonics that it's creating is causing cavitation in the water and in the solvent that we have. That cavitation is really helping to get the drug into solution, but it can also cause cavitation and nucleation of gases in your blood if it was at a high enough power. Now, I don't know if this one is at a high enough power, but a general rule is you don't hold with your hand or put your hand into anything into a sonicator bath. You let a clamp do the job because you don't want to risk any health issues. So you put it in there and then you switch the dial on to turn it on. Now, they can also be heated because you may need to heat your sample to get it to go in, but when we're sonicating, if we sonicate for a long time, we might end up heating a little bit anyway. We're not going to heat this. And just bear in mind, we're using a low boiling point solvent. If we go for too long without monitoring it, we may find that we start to have the top popping off. Or as has been the case, and I've seen it in the past, we have some relatively nasty things that start flying everywhere because someone has heated it, forgotten it's heated, walked away, come back, touched it, caused a load of nucleation, and then the solvent's boiled over. And typically those people aren't wearing the protective clothes they need to wear, says a man speaking from seeing it. Okay, so all we do is just switch it on and let it go. I'm doing all the talking now because as I turn it on, it will be noisy. So I'll leave it on just for a second and then we'll move back to the fume hood. I'll turn the camera off and we'll move back to the fume hood once it's all dissolved. So I'm just going to move the camera in here, just so you can see. But we do, in fact, this is quite a strong bath, actually, stronger than I had imagined. We do indeed have cavitation in the solvent there, and you can see that it's forming bubbles inside the flask. And there we have the exact safe reason why I shouldn't plunge my hand into this bath. So, actually a perfect example there, and we do need to be careful that this doesn't start to boil, in which case we would need to make sure we loosened off the lid so we didn't have any pressure build up. I'm now back from the sonicator and I have my now dissolved trimethoprim in DCM in here. I also need to have 100 millilitres of 0.001 molar hydrochloric acid, which I've previously measured out in this measuring cylinder here. So, next step is to get the DCM into the separating funnel. Now we need to make sure before we put anything in the separating funnel that it isn't in the open position. Obviously all that will do is come straight out. And typically you'll find them left in the open position because people have left them to dry. So always check that first. And then be able to open this up and pour my trimethoprim and DCM directly in. Open so we can vent, and then we need to have the hydrochloric acid poured in afterwards. This is why I previously poured it, so we don't need to bother clamping this up and measuring it out again. So we can get that straight in there. So this is a really good point to note which is on top, the water or the DCM, if you don't want to have to look up the specific densities of it, to make sure you tap off the right ones. So hopefully you can see there we've got two distinct layers. I think that's pretty clear. And we've got the DCM and the water. Okay. Now, we want to give the opportunity for the trimethoprim to dissolve in either phase we have here. And whilst we've just got this interface here, we haven't got much opportunity for diffusion across the two phases to happen. So the next stage is to stopper this separating funnel and to shake it. Now, I'm going to do this outside of the fume hood, and I'll move the camera so you can see, but when you mix these two solvents, you often find there's an energy change from mixing, because they're not fully mixing, but you're still getting a bit, and you might get an overpressure. So the first shake I'll do may end up popping this stopper off. So before I take this out, I will do a little bit of shake in here first, and then just release any pressure. And it's advisable to do that periodically when you're shaking two immiscible solvents to do a separation or to do a log P. So that needs to be shaken for a little while, because we want to give every opportunity for the trimethoprim to really get to its equilibrium state. So what I'm going to do is I'm going to shake that for a few minutes. Okay, so now you can see that that looks like a single phase, in fact. If we put it back inside the cabinet, be able to get a better view. It did look like a single phase, and you can see now splitting, but this top phase is still looking quite cloudy because we've made sort of a very unstable emulsion. And so we're going to leave that in here to fully separate. And that may take a good few minutes. So whilst that's separating, we're going to go over and set up our calibration on the UV vis of trimethoprim in an aqueous solvent, so that we can determine by UV vis how much trimethoprim we've got in the aqueous phase on here. Whilst the DCM and water are separating and the trimethoprim is coming to equilibrium across the two phases, we're going to set up and determine a calibration curve for trimethoprim in sodium hydroxide, in 0.1 molar sodium hydroxide, because this is what we're going to be diluting the aqueous phase with later on when we then come back to take the UV vis readings. So we're going to use this as a solvent, and we're going to make the calibration curve so that we know what concentration does a certain absorbance correspond to when we do that later. So we can work backwards and then determine the concentration of trimethoprim in the aqueous phase, and therefore how much is also in the DCM phase as well. So to do that, we're going to need various concentrations of sodium hydroxide with trimethoprim in it, so various concentrations of trimethoprim in sodium hydroxide, I should say, and then we need to take their readings. And the wavelength we're going to do this at is 287 nanometers. So I'll just set up the UV vis to just do a single wavelength, 287. And we're going to do this, rather than making up lots of different concentrations, we're going to make up the one largest concentration and then do serial dilutions. So I've got 50 milligrams of trimethoprim weighed out here accurately, and I'm going to put that into this first beaker. And then I'm going to take 20 millilitres of sodium hydroxide solution. To dissolve that trimethoprim in. Okay, so I'm not actually quite sure how long that will take to dissolve, so just have to give it a bit of a stir, and whilst that's dissolving, I'm just going to get another beaker to decant some of this sodium hydroxide into. And then once this has dissolved, what I'll be doing is I'll be taking 2 millilitres of this solution and diluting it with another 8 millilitres of sodium hydroxide to make solution B. Then I'll be taking 2 millilitres of solution B, diluting it with 8 millilitres of sodium hydroxide to make solution C. And repeat that 2 more times with C and D to make all of the different concentrations that I'll need to make a calibration curve of the absorbance of trimethoprim in sodium hydroxide 0.1 molar, so we can take an unknown and work out what the concentration is. Okay, so now that's dissolved, I'll do my serial dilutions. So I want 2 millilitres of this. And I'm just going to top this up to 5 millilitres in the measuring cylinder. And measure out another 5 to get the 8 millilitres of sodium hydroxide to give us a 1 in 5 fold dilution. And there we have it. We have 5 serial diluted concentrations with which we can take our measurements to make a calibration curve. And so all that remains to do in the lab is to blank the spectrophotometer to our sodium hydroxide. So we tell the machine to ignore essentially the absorbance of the cuvette and the solvent. That's what we're doing when we blank. And then I'll just take a reading of that just to make sure that that's fine. And it's reading as minus 0.003, which is within the error of the instrument. So we know that's we'll be going through the origin with our calibration curve. And now what I'm going to do is, using this same pipette, I'm going to start with the lowest concentration and work my way up to the highest concentration. In doing so, I can just use the same pipette filler because I'm not contaminating the lower concentrations with the higher concentrations, and all I'll be doing at worst is the tiniest little dilution of these. So in practice and generally, you can just do this. It's absolutely fine. Okay, so there we have those. I've noted down the measurements and I'll share those with you so you can use those as well to work through this properly. But I'll be taking a few more averages to just get you the best results possible for that. So now the two liquids are separated in the fume hood, and we'll be going over there again to tap off the two different phases and dilute the one phase so we can get a reading for the absorbance. So now we've done the calibration, you can see that we've got two separate layers here. What you might be able to see is that we've got some bubbles here. We've got some bubbles here that belong in the other phase. And you can sometimes remedy that by giving a little tap on the side. Okay. So a few of those have gone, a few of those have stayed. I think we've probably reached the point where I can't remedy that any longer. So just secured that a little bit higher. So now I can drain off the two phases, make sure that I keep them separate from each other. So I'm just going to sit down so I'm at the right height to do this. Do also make sure that you take the lid off, otherwise you get that gloopy action that I just had there. So we're draining off the more dense phase. Now remember, you can look up specific densities and make sure you know which phase is which, because we don't want to be putting the DCM into a plastic cuvette to take its absorbance reading. Okay. So there we have one phase, and now I can be a little bit less cautious to just drain off the second phase. There we go. So we have the two phases that we have separated out, and we're going to be taking the aqueous phase over to the bench to dilute it with sodium hydroxide and take a reading of it. So we're back out, and I've got the aqueous layer here ready to be diluted, because this will be too concentrated for the calibration we've done. So I'm going to take 5 millilitres and dilute that in a volumetric flask to 100 millilitres. Giving us a 20-fold dilution and hopefully putting it in within the calibration zone of what we've done already. So a calibration is only as good as its limits. So as soon as you start assessing concentration outside of where you set your calibration limits of maximum concentration, you start to introduce more error into what you've done. So this is the 0.1 sodium hydroxide, 0.1 molar sodium hydroxide. Now at this stage, if you're not 100% sure, still just worth checking that you've got the right phase, because we're in glass, and you can see that I haven't got two phases, I've got one phase. It's mixing, so it's definitely the aqueous phase. It's always worth doing these checks, because the next stage is it's going to go into the plastic cuvette, and that's would be worse if it were to get through the plastic cuvette and cause damage to the spectrophotometer. Just using a pipette to get up to the line to make sure that it's nice and accurately at 100 millilitres. Now, before you do anything with this sample, we must mix, particularly in a volumetric flask, because the stuff in the neck is unlikely to have diffused in the time it takes you to pour in up to the volume. They're not designed for diffusion, they're designed for precision. So we make sure that's nice and mixed. We've got our dilute sample, and now we can take a sample from there, and in our already set up and blanked UV vis, take the measurement, which has come out at 0.646, which I'm going to write down. And I'm going to just take a couple more, just to make sure there wasn't a power fluctuation or anything when I first took that measurement. And they were all around the same ballpark, 646, 644, 646. And there we have it. The next part is going to be done outside of the lab. We're going to take the results, which I'll share with you to do the calibration, and then we'll be able to determine the concentration in the aqueous layer of that partition coefficient experiment, and then do a little bit more analysis and thinking after that. I'm now out of the lab and I'm back home, so we can go through the questions at the end of your lab script and do the relevant analysis and have a think about what that data means. So I shared with you on Blackboard the data that I got from the lab for the calibration curve and for the absorbance of the aqueous phase in the log P experiment. And that's in a Excel spreadsheet, which I'm now going to share on screen with you now as well, so you can follow along with the analysis that I'm going to do. Hopefully you can now see that on your screens. So we can see we have a spreadsheet here where I've got the calibration data, which has got all the different solutions that we took the absorbance of at 287 nanometers. So we've got the blank, which is just the water, the aqueous phase, sorry, and the cuvette. And we've got the 5 different solutions that we made by serial dilution of a known concentration of trimethoprim. And then underneath that, we've got the original mass of trimethoprim, which is the other data that we know. And we will also know the absorbance of the aqueous phase that we did experimentally, which was 0.464. 646 even, not 464, 0.646. There it is. So the first question you've got to do in the lab script is, using the calibration produced, what was the concentration of the trimethoprim in the aqueous layer? Okay, and it says, remember that we diluted the sample, so take that into account. So what we've got here is we've got the data from the calibration, and we now need to work out what is the equation for determining the concentration of an unknown solution based on its absorbance at 287 nanometers. And so to do that, we'll just need to make the calibration line. Now you can see here that at the higher concentrations, at 200 and 1000 milligrams per litre, that the UV vis wasn't able to take a proper reading. That's because the concentration was too high, and effectively we blinded the machine and blocked all of the lights coming through. So it was unable to take the ratio of incidence light and transmitted light to give us an absorbance. So we're going to have to ignore those 2 values. So just to make that clear, I'm just going to make those red. We need to ignore those. So what we've got is we've got 4 values, including the blank, which would be at 0. Of known absorbances and known concentrations of trimethoprim in the aqueous media. And we need to insert a scatter plot for that. You can do this by hand if you wish on graph paper, but I'm going to do it on Excel because it's quicker and more accurate. And then we need to fit a linear line of best fit to this. So a trend line, linear. We can see there we've got a relatively nice trend line. We've got some of the data points are slightly above and below that, but that's fine. That's natural variation in what we're doing. That's to be expected. And we need to know the formula for that line, which will tell us the relationship between absorbance and concentration. And you can relate this all the way back to Beers-Lambert law if you so wish. Hopefully you've done that in the past. So I'm going to display the equation on the chart for this line. And I'm just going to make that a little bit bigger so you can see it on the screens. Hopefully easier. There we are. So this is the relationship between concentration of trimethoprim and absorbance at 287 nanometers in aqueous media. If I'll just zoom out a bit again so we can see everything. This will now tell us what concentration our sample was at, our unknown sample was at from the aqueous phase. So that's done with this here, with the gradient of the line. We're going to ignore the intercept because the intercept should go through 0. So, and we can see that that's essentially negligible. So we're going to ignore that. And so the factor we need to times these numbers by is 0.0266. Now that's y equals 0.0266x. And on the x-axis, we've got concentration. On the y-axis, we've got absorbance. Now we've started out with absorbance. So to get to concentration, we need to divide that by 0.0266. So the dilute concentration of trimethoprim in aqueous media is equal to 0.646 divided by 0.0266, which I've just taken from the gradient. And we've got a dilute concentration of 24.29 milligrams per litre. Now remember, we diluted this sample so that we could take the reading in the UV vis. And that's because the concentrated sample may well have been too concentrated to get an accurate reading. And remember, if we go too concentrated, we effectively blind the UV vis because you block all light going through and some light needs to get through for the UV vis to work effectively. And in the experiment, if we refer back to exactly what we did, we will see that we took, let's have a look, we took 5 millilitres of the sample and diluted it to 100 millilitres. So that's a dilution factor of 20. If you're unsure how to get that, the way you can reach a dilution factor is you take the final volume that you end up with and divide it by the amount of more concentrated, the mother sample, that you put into that. So in our case, we had 100 millilitres of the final sample size and we had originally put in 5 millilitres of the more concentrated mother sample. So that would be 100 divided by 5, which is 20. But you can also just work that out intuitively as well if you can do so. So we've got a dilution factor of 20. And so the original concentration will equal the dilute concentration times the dilution factor. So our original concentration was 485.7 milligrams per litre. And we had 100 millilitres, which is 0.1 litres. Okay, and that means that we had a mass in there. So the total mass in solution of that is equal to the concentration times the volume, which means that we had a mass of 48.57 milligrams in total in that 100 millilitres of sample in our separation funnel in our log P experiment. So we've gone further than what that question asked now. So the question had asked, using the calibration produced, which we have here, what is the concentration of trimethoprim in the aqueous layer of the log P experiment? Well, the concentration was 485.7 milligrams per litre. So let's move on to question 2. Given that the aqueous layer was on 100 millilitres, how much trimethoprim is contained in the aqueous layer? So we've done that already. I've moved on and did that already. So we know that's the concentration in milligrams per litre. And so to find the mass, we need to know the volume in litres, which was 0.1 litres for 100 millilitres. And you simply times the two together to get the mass of trimethoprim, and that will be in milligrams, which I've not labelled on here. So there we go, in milligrams. So we had 48.57 milligrams in the aqueous layer of our log P experiment.
Given that 0.5 grams, this is question 3 now, was put into the system originally between the DCM and the water, how much trimethoprim is in the DCM? First part of question 3. Well, so 0.5 grams is 500 milligrams, and we are working in milligrams on here. And I put that here. So original mass of trimethoprim in milligrams was 500. So the mass of trimethoprim in the DCM phase, it won't have disappeared. We can just do that by difference. So we know we put 500 milligrams in originally, and we know that the aqueous layer contains 48.57 milligrams. So therefore, the DCM phase must contain 500 milligrams minus whatever there was in the aqueous phase. So 451.43 milligrams. And we can see that answer there now. Hopefully that makes sense. We've worked out the concentration in the aqueous layer. From the concentration and the dilution factor, we've worked out how much mass there is in the aqueous layer. And from that, and knowing how much trimethoprim we put in originally, we can, by difference, determine exactly how much was in the DCM phase, the organic phase of the log P experiment. So carrying on with question 3, and given that 100 millilitres of DCM was used, what is the trimethoprim concentration in the DCM? So the volume that we used was 0.1 litres. Let's all stick in the same units on here. So 100 millilitres, 0.1 litres. And so the concentration is simply the mass that we used divided by the volume. And so we have a concentration of 4,514 milligrams per litre. And the original the concentration of the aqueous phase was 485.7 milligrams per litre. And there we've got two directly comparable concentrations that are in the same units of milligrams per litre. So we know how much trimethoprim was partitioned between the aqueous phase and the DCM phase at equilibrium. And now we can move on to question 4. Assuming that the trimethoprim was unionized at this pH, what is the log P value? And you can use equation 1 in your worksheets, which is simply just the equation for log P. And the way we're going to do that on here is just using these two concentrations. So this one and this one. So the log P is going to be equal to the log to a base of 10, the rate of the ratio between the concentration of the DCM phase divided by the concentration of the aqueous phase. And we get a log P value of trimethoprim, assuming this is all unionized and we're not taking into account ionized species, we'll get a log P value now of 0.97. And that tells us that this drug is predominantly partitioned into the organic phase, the DCM phase. Of course, we know that already by looking at these, but now if we hadn't done this experiment and we looked at that log P value, we know, well, that's above 0 and it's nearly 1. So we know that there's going to be quite a lot more trimethoprim partitioning itself into an organic phase compared to an aqueous phase. So this drug will preferentially, at an unionized form, partition into organic phases over aqueous phases. It doesn't mean it isn't soluble in both. It clearly is soluble in both. But given the choice in a partition experiment, it will preferably go into the organic DCM phase. And that's what that tells you. And indeed, if you look up the literature values of the log P for trimethoprim, you'll find that they're around about 0.9, 0.91. And so that's pretty good for a one-off experiment in a lab to get a value that's that close. That's pretty good. And so that's what we can determine from that in the lab. Now, log P is then useful for determining where and how drugs may or may not be absorbed, or how they're going to act in different compartments of your body. Something that's more useful, though, particularly for absorption and particularly through the gastrointestinal tract, is log D. So, as hopefully you now understand from lectures and from the lab, is that log D does the same kind of thing as log P, but it will do it at any pH because we'll take into account unionized and ionized forms of the drug. And so we can then take log D values at any pH, and we can see what difference pH has on where a drug will partition, or a molecule will partition itself between oil and water at any of those pHs. So question 5 says there is some example data for log D, and that's again on the spreadsheet that I've uploaded onto Blackboard, and I've now put that on the screen for you as well. Can you identify where the two pKa's are for this molecule? Okay, so this is still using trimethoprim, and trimethoprim is a molecule with some basic groups on it. So it's got some amines on the molecule. Look up the structure of the molecule. Now, one thing we know about solubility is that like dissolves like. And so an aqueous layer is more likely to dissolve something that is charged, and an organic layer is more likely to dissolve something that is uncharged or isn't polar. And so when we look at log D across different pHs, where we get a big switch in log P, a big change from aqueous solubility to organic solubility, or organic solubility to aqueous solubility, that will typically be at the point at a pKa of a group on that molecule, because that will be the point at which the charge changes dramatically. Now, pKa, remember, is the pH at which a group is 50% ionized. And when you go 2 pH points above or below that, you have complete ionization or complete not ionization for that group. That depends if it's an acid or a base. Now, we're looking at basic groups, and so when you go below the pKa of a base, we get the ionized form of a drug, of a molecule. And so we're going to find that it becomes more water soluble when you go below that point, because it's charged and therefore more water soluble, because water likes to dissolve things that are charged. And that's what we're going to be looking at in this data of log D, which, remember, is the partition coefficient at various different pHs. So if we plot this data, you'll be able to see what I'm talking about far more readily. So I'm going to plot it as a scatter plot with just a line that connects the points up. So here on the x-axis, we've got pH. We've got pH 0, 1, 2, 3, 4, 5, 6, 7, and 8. And we've got data between pH 1 and 7. On the y-axis, we have the log D. So just the same as log P, this is the partitioning between organic phases and aqueous phases. So if we're above 0, we're preferentially going into the organic phase. And if we're below 0, we're preferentially going into the aqueous phase. And 0 would be a 50-50 split between the two. And as we can see here, at pH 7 and pH 6, we've got pretty much the same data as you had before. So you found the log P for trimethoprim, which was 0.9 something. And so at pH 7 and 6, clearly this is in its unionized form, this trimethoprim, in this made up data. Can't stress enough that this is made up data. We can see that it's at its log P value here. So we know that it's partitioning mainly into the organic phases. But when we get to pH 5, 4, and maybe around 3, but pH 5 and 4, you can see that there's been quite a dip, and that we're almost getting a 50-50 split between aqueous and organic solubility. And that's because we'll have charged 1 or 2 of the basic groups on the trimethoprim molecule. And so here we're moving towards aqueous solubility. We've got to a low enough pH to protonate and charge the basic groups on trimethoprim at this point here. So we can say the pKa, one of the pKa's on trimethoprim in this made up data, again, don't quote this, is between 5 and 6. So the pH at which 50% of the groups become ionized, i.e. the pKa, is between 5 and 6. And then we have a second quite dramatic drop where we have the other groups becoming ionized on trimethoprim between pHs 3 and 2. So below pH 2, we've got everything is ionized, all of the basic groups have got an extra proton, we have an incredibly ionized molecule, and so it becomes incredibly water soluble instead of soluble in oil or organics. And so we can say then that the two pKa's of trimethoprim based on this data are between 5 and 6, and 3 and 2. And that's because the pKa is an indicator of when a molecule will charge and not charge. And the charge on that molecule will greatly influence its solubility. And so when we cross a pKa, when we're looking at the partition coefficient at different pHs, we'll get a massive change in solubility. And that's exactly what we see here in the change in log D. So moving on from there, question 6. Using the same data as in question 5, and given a log D/P value is around 0 to 3 for optimal absorption of drugs through the gastrointestinal tract, what pH range then would give optimal absorption for trimethoprim? So using the same data as in for question 5, so this same data, and given that we need a log P or D value of between 0 and 3, what's the optimal pH range for absorption of this drug? So the log D is on the side here, and we need it to be between 0 and 3. Well, this chart only goes up to 1.5. And so we can see that it reaches 0 at pH 4, and then above pH 4, it's always within that 0 to 3 range, within the data we've got. So we can confidently say that within the pH ranges of 4 to 7, trimethoprim is its solubility is such that it is suitable for absorption through the gastrointestinal tract. This is very simplified. This is only based on passive absorption, and it's just that the solubility is such that it can go into the water phases in your gastric juices, it can get through the oil phases of your cell membranes, and then through the aqueous phases of your cells again. So that's why we need a balance between the two, and ideally it needs to have slightly more oil solubility, which is why we're looking for 0 to 3 on the log P log D scale. So a pH of 4 to 7 based on this data would give optimal oral absorption from trimethoprim if you took it as an oral dosage form, like a tablet or a capsule. So now that you know that we need a pH of 4 to 7 for absorption of this drug in the gastrointestinal tract, let's take a look at this little schematic, this very simplified schematic of the gastrointestinal system. We've got the stomach, the small intestines, where they've just put the jejunum and ileum on here, but we might also put the duodenum on there, maybe. And then we've got the large intestines going to the colon. And through there, we've got the different pH ranges that you might encounter going through the gastrointestinal tract. And this is question 7. So using this information and the fact that we know we need pH 4 to 7 for trimethoprim to be absorbed, where would you start absorbing trimethoprim in the gastrointestinal tract? And that's just a simple case of following it through. So if we'd eaten, and if we hadn't eaten, we're going to get two different answers. So let's start with a fasting. So you might often be told to take a tablet on an empty stomach, and this is what trimethoprim would encounter. So in your stomach, you'd have between pH 1 and 2. Now, between pH 1 and 2, we've got a log D value of -3. So that's not within the 0 to 3 range, so it's not going to be absorbed there. And then we'd go through the duodenum, which we don't have information for, but it will be around about pH 3 to 4 maybe. And then in the jejunum, we've got pH 4.4 to 6.6. And that is within the pH range we need to get the trimethoprim in the ionization state that it needs to be to have the correct solubility for it to be absorbed correctly through your bowels. And so we can say that from the jejunum, this will start to be absorbed. And we can also then confidently say it will continue to be absorbed through the rest of the bowel because the pH does not rise higher than what would take the log D value to be too high itself either. So when you're fasting, you would start to absorb this drug from around about the jejunum, somewhere near the beginning of the small intestines. And if you had eaten, so if you took this drug with food, the pH of the stomach may rise enough that you start to absorb it effectively in the stomach itself. So if you have enough food that neutralizes enough acid in your stomach, so maybe if you took this with some indigestion remedy that neutralized the acid in your stomach and you went up to about pH 4, then you would actually start absorbing this drug from your stomach and then all the way through your intestines. So hopefully that puts everything into perspective for you. So you started out just doing a log P experiment where we've taken a known drug, trimethoprim, and seen how it partitions itself across DCM and water. Now, more typically, we might use octanol, but we've used DCM in this case. Then we've made a calibration curve to determine the concentration in each phase. And with those different concentrations, we've been able to determine the log P, which is 0.9 something. And then we've gone on, I've given you some data, which is made up data about how that partition and solubility changes at different pHs due to the changes in ionization of the molecule. And then the real world impact that that will have, for example, on where you may or may not absorb a drug after you swallow it, and why it might be important to manipulate these things to get good drug delivery or good drug partitioning across various parts of the body.